yes, bosonic error correction is the topic. And before I get started, I'd like to acknowledge the people of the Wairong and Bunurong language groups of the Eastern Kulin Nation. They are the traditional owners of the land on which I'm broadcasting from today, and I pay my respects to their ancestors and elders, past and present. I am a chief investigator in CQC2T. I'm also one of the leaders of the Kermit group. You can see I've got, oh, hang, where is it? Kermit behind me. This is just some shameless plug for this new group at RMIT. The new is in the last couple of years. We've been building up to something great. But this talk is not about what we do specifically. So I will encourage you to visit the website if you're interested. But I'm going to go on and talk about classical error correction. So we're going to start here. So I want to start with, obviously, cats. So if you have a picture of a cat in a digital file in your computer, and if you have one printed on a piece of paper, they look the same. You put it on the screen, looks fine. On the piece of paper, looks fine. It's a good printer. But if you make a photocopy of the printed printout of the cat, there's a bit of noise that's added. There's a bit of junk that appears, a bit of spots. So some of the blacks don't turn a little bit lighter, and some of the whites end up with black spots on them. And so this is noise that gets added. Whereas if you copy the digital file in your computer, there is no noise. So importantly, if you copy this multiple times, if you copy the copy and then you copy that copy, etc., you end up building up a lot of noise to the point where I mean, you can still see it now, but it's hard to distinguish detailed features. For instance, you can see the whiskers. You can certainly see the outline of the cat because the lines are quite thick. You can see the whiskers because they're reasonably thick, but you can't see very clearly the lines under the eyes or these little dots here by the nose. Those are completely gone. Those fine details have been lost. So some of the information survives, but a lot of it's been lost. But an important question is, why does noise build up in the photocopies, but not in the digitally copied files? There's a couple answers for this, but you'll see what I'm getting at. What I want to talk about is error correction. So tiny mistakes in the copying process. These are known as errors or noise. Noise we think of as in your ears, loud, but noise is anything that disrupts communication. So in this case, it's visual communication, and the disruption is the speckle pattern that appears when you copy it on a photocopier. Tiny mistakes happen in both. Photocopiers, however, there's no way to correct the copying errors. You just get what you get. It does the best it can. You get a new printout of the photocopy, and then that's it. There's no checks to see whether it was correct or not. It just that's what you get. Digital files, however, the computer hardware detects and corrects copying errors to the best it can. Now, another difference, of course, that's what this note is about, is that the error rates are different between the two, and that photocopying will introduce more noise to even without error correction than copying a digital file. That's a difference in the hardware. So that's also a way to improve the performance of whatever system you have. It's just design better hardware. Sure, you can do that. But what I want to talk about is the way that actually involves a digital error correction. So the main question is, how do we improve the fidelity of copying or processing information? So as I mentioned, one way is just improve the hardware. And so this would, in quantum computing parlance, be improving the coherence times of your systems. And for instance, digital copying of a file has fewer errors than photocopying, so that's a hardware improvement. But we also have data robustness. So I noted before that thick lines are more resilient to copying errors than thin lines, and the same information can survive a small amount of noise if the line is thicker. And redundancy, therefore, in the thickness of the line provides robustness to errors. And this is what I want to get across here. The notion of redundancy is just making the line thicker. So in a simple case, we want to digitize our information, and then we want to use an error correcting code. That's the technical term for essentially what's going on here with these thick lines idea. So what we do is one simple type of code to illustrate. This is a repetition code. So for every 0 that you want to send in your digital message, you send 3 zeros, and for every 1 you want to send, you send 3 ones. Okay, so this repetition code is like a thick line. It thickens the amount of information that you are sending per bit of logical information. So what happens is you encode a single 0 into 3. If one of the bits gets flipped, that's an error. If you didn't encode it, then you'd be screwed. You'd have an error. You'd have a black speck when you should have a white speck. If there's only one error, you take a majority vote between the three, and you say, well, that should be 3 zeros, because 001 is not a valid code state. It's not one of the three that are valid. And so you correct it, and then you decode, and it's right. So this 3-bit repetition code can correct one error. But if you do the same thing and you get 2 bits flipped, then you take the majority vote, and instead of flipping these 2 back, because you don't know what happened, instead of flipping these 2 back, you say, well, it's more likely that the center one got flipped from a 1. And so you incorrectly perform the correction, attempted correction, and you get something that's not right. So when you decode it, you still end up with an error. And this is a feature of all error correcting codes. There's going to be some errors that are always catastrophic. Well, they're not catastrophic necessarily, but they're going to leave you with residual errors. So a 3-bit repetition code can correct one error, but not 2, just 1. All right. Longer repetition codes can correct more errors. So in this case, I'm just taking a 0 and replacing it with 9 zeros, and a 1 replacing it with 9 ones. In this case, if you're using the majority vote method, then any of these 4 being flipped will not produce an error, because the majority vote says that everything's fine, should be all good. So you end up saying that there's more zeros than ones, and so you correct that to the all 0 state. So a 9-bit repetition code can correct 4 errors. Okay, but there's another way to make a longer repetition code, and that's to concatenate. And I want to explain concatenation because this concept is important in quantum error correction. So what we do is we encode this once, and then we take each of these 3 and we do it again. So it looks like this. So you take your original 0 that you want to send, and you encode it into 3 zeros. And then you take each of those and you encode those into 3 zeros as well. And that's really important, because now we have 9, but they're grouped into blocks. So in this case, if we have 5 errors, and they're in this particular pattern, or similar ones, where you have 1 error here, 3 errors there, and 1 error there, you can actually do the majority vote within the blocks, decode the blocks, and then do the majority vote on these, and you see that you get the right result. Whereas normally 5 errors, if this were just treated as the 9-bit repetition code before, you'd have an error, because it's 5 ones outweighs the 4 zeros. But because of this organization, you can actually handle sometimes some combinations of 5 errors. Now, of course, if this one were over here, then you'd have 2 blocks. It thinks it's a telephone number. Sorry about that. You'd think that these 2 blocks would be 111, and you would end up with a logical error. So not every 5-bit error is recoverable, but some of them are, and that's a nice improvement. Okay, that's great. So what else do you need to know about this? Well, one thing is that when dealing with error correction, classical or quantum, you want to keep the information encoded, because anytime you have a single individual 0, it's vulnerable. But when it's encoded like this, it can suffer a couple errors here and there, and the error correction procedure will fix them. And so you want to keep the information encoded. So you want to just treat this collection of 9 zeros as a logical 0. And then when there's error, then periodically you correct for errors that build up. And hopefully you do that often enough so that they don't build up into actual errors on your encoded data. And of course, once you have this, you need logical operations that act directly on the encoded information. So you don't want to have to encode and then decode to switch the bit from 0 to 1, for instance, if you're doing an addition. You want to have the logical operations, the addition, subtraction, multiplication, division, whatever you're doing with these things, be done at the logical level. So dealing with these code blocks all together rather than having to decode. All right, so let's move on to quantum error correction. What's the main difference? Well, classical error correction often relies on redundancy, which is cloning. You take a single piece of information, you make multiple copies of it. That's not the only way that it does it. There's also parity checks and other things. But that's an available tool that you have with classical data. You can also measure it to take the majority vote. You just measure all the bits. Okay, that's good. But in quantum information, if you're processing quantum information, you don't have cloning available. You cannot make multiple copies of an unknown quantum state. There's a theorem that says you can't do that, Nova theorem. And quantum information is destroyed if you directly measure it. If you directly measure the bit values, then you destroy any coherence that those qubits had with the other qubits elsewhere, and you destroy any coherence between them, and so it's useless for quantum computing. So you don't want to measure the actual, I said bit values. What I mean is you measure the qubits in a particular basis and you get a bit value. You don't want to do that. Okay, so what can we do? Well, essentially, we replace cloning with entanglement. And we use parity measurements because we don't actually need all of the values of the three you don't need all three bit values. All we need to know is, all we need to distinguish is between same and different. So I'll show you on the next slide. So in a quantum repetition code, which is corrects against one type of error, you take a single qubit and you encode it into a single zero and you encode it into 3 zeros. Now I'll say what this, I just said you can't clone, but if you know what state you have, you can make 3 copies of it. So if we have an unknown state, so you have some superposition, someone has made this and handed it to you, you can't make 3 copies of that because you don't know what it is. Well, what you do is you can do a unitary circuit that takes you from this to this superposition. So it's the same coefficients, alpha and beta, but now we replace the 0 with 3 zeros and replace the 1 with 3 ones. And there is a unitary circuit, a unitary operation that will do this, but this is not the same as 3 copies of the initial state, which is what this would be. Notice that in this, you'd have products of alpha squared and alpha beta and betas. Anyway, we don't have any of that. We just have 1 copy of alpha, 1 copy of beta in this superposition. Then if one qubit gets an X error applied to it, then instead of being in a superposition of 3 zeros and 3 ones, you have a superposition of 001 and 110. That's not right. That's not what we consider to be a valid code word. But we don't want to measure the individual qubits because doing that would destroy the superposition. So what can we do? Well, we non-destructively measure parity. We can come up with a circuit that measures, are these 2 bits, these 2 qubits the same when you measure them in Z? Are these 2 qubits the same when you measure them in Z? And you'll see that in both cases, the answer is yes and no respectively, whether it's the one on the left or the one on the right. And from that information, you can say, okay, well, then we should probably flip the 3rd one. There's probably an error on the 3rd one. So we don't actually have to know whether we have 001 or 110. All we need to know is same for the first 2, different for the second 2. And based on that, we flip the 3rd one. And then we can decode again, unitary circuit, and we get the correct answer. So this is a 3-qubit repetition code, and it can correct 1 X error. But we want to keep the information encoded. We don't want to have to encode and decode. So we need logical operations that act on the encoded information. And this is really important because it's not just about protecting against errors. It's about, can you do logical operations on your information? Also, what about Z errors? Well, quantum errors always come in at least 2 flavors, X and Z, and you have to correct both to be robust to quantum noise. So the 9-qubit Shor code is just the 3-qubit repetition code for X, concatenated with the 3-qubit repetition code for Z, and I've shown them here. And that's all I'm going to say about it, because I'm just giving a flavor of this quantum error correction. So fault tolerance is the difference between error correction and fault tolerance, is that error correction is just trying to protect against noise. And fault tolerance is succeeding. Fault tolerance is when the initial noise is low enough, error correction works in that it lowers it even further so that you can concatenate further and use bigger and bigger codes to reduce the error rate as low as you want. The maximum level of tolerable noise is the fault tolerance threshold. And typical thresholds are about 0.1% to 1% error rates. So let's move on to bosonic error correction. This was just qubit error correction in general. But in optical quantum computing, there's a whole quantum field to play with, the electromagnetic field. We don't just have qubits. We have an entire field, which is many degrees of freedom. And each mode of this bosonic field, like the electromagnetic one, is an infinite dimensional Hilbert space. And this is often missed when thinking about single photon encoding. So I really want to stress this point, that you always have an infinite dimensional Hilbert space to play with, 1 for each mode. The Fock basis is states of exactly n photons in a given mode. But we also have another basis, the position basis, which are eigenstates of A plus A dagger. And this is the usual basis for wave functions. And so every mode of a Hilbert space can be described using a wave function as well. There's many possible types of errors: photon loss, thermal noise, displacement noise, etc. And bosonic codes encode qubits into modes, and sometimes, hopefully, protect against noise. I've defined bosonic codes slightly differently than they're used today to make a point that I'll get to in a minute. For illustration purposes, I'll consider photon loss noise. So this is going from n photons to n minus 1. Can you correct that error? That's the question. Well, the single rail Fock encoding uses these two states. So there's the 0 state, the logical 0 state, this blue one, is just a single Fock state, 0, the vacuum. And the logical 1 state is having 1 photon. So the Fock state 1 within the mode. But notice there's a bunch of there's a whole Fock ladder here. So, and we're just not using that. So we're assuming we have at most 1 photon. So loss causes an amplitude damping channel where 1 goes to 0 and 0 stays at 0. And that's a type of error, and it offers no protection against it. So this is what's known as a single rail encoding. And on the right, I've shown the wave function for the vacuum state and for the n equals 1 Fock state. This is not the Wigner function. Sometimes that's shown in Wigner function. I'm going to focus on wave functions. The photonic qubit, which is used in linear optics quantum computing, this is the most traditional single photon encoding, is to put a single photon in one of 2 modes. So this is the logical 0 state, the blue, and this is the logical 1 state, the red. I'll show you what we have. So in mode 1, we have exactly 1 photon, and in mode 2, we have exactly 0 photons. And again, we ignore the rest of the Fock ladder, but it's always there. On the right, it's the same thing. On the right, it's the same thing in wave functions. This is n equals 1 photon. This is n equals 0 photons, the vacuum. Okay, and then so that was the logical 0. The logical 1 just has these reversed. So the photon finds itself in mode 2, and there's vacuum in mode 1. So photon is in mode 2, vacuum in mode 1. Photon loss causes an erasure error because now we have vacuum, and that should never happen. It just means your photon's gone. So you can't correct that, but it's an error detecting code. As in, if you measure both modes and you get no photon anywhere, well, you know that an error has occurred and you cannot recover from it. That's still useful, error detecting code. We can do a little better, though, and actually correct things. So there's something called a binomial code, which is from this paper. I know it's hard to see, but anyway, the slides will be available, I'm sure. So a binomial code takes the photonic qubit and says, all right, well, what if we put a little bit of space between these states? So this is the 0 state. It's an equal superposition of, the logical 0, equal superposition of no photons and 4 photons. And it has a wave function that looks exactly like this. I plotted this. This is a rigorous plot. I haven't put the axes on here, but you get a sense of how big they are from the previous plots. And the logical 1 state is exactly 2 photons. So here they are together. What's important is if you have a single photon that gets lost, then 4 photons becomes 3, and 2 photons becomes 1, and you never get 0 anymore. That's reflected over here by the fact that these wave functions are even. If you flip them left to right, where is it? If you flip them left to right, they look the same. So if you lose a photon, you get an odd wave function. And you can detect that. You can measure parity and realize, oh, damn, I've lost a photon. So you can actually correct that because it preserves the superposition. So we've gone from no protection to error detection to error correction of a single photon being lost. There are other types of encodings. Coherent-state encoding involves just saying, well, this displaced vacuum state or a coherent state is my logical 0, and this one is my logical 1. Now, some of you may be used to seeing these in terms of a Wigner function, but I want you to think about this in terms of a wave function. A wave function of a coherent state is just a displaced vacuum state. You take the vacuum state, you just move it. So in this case, I've shown alpha equals 3, and this looks pretty good. That's fine. But if you have smaller alphas, you have a problem here, which can be dealt with. But what's important is that these basis states are now non-orthogonal. And this leads to measurement errors, because you try to distinguish between these two, and sometimes you can't reliably distinguish them. That's a different type of error model, and it needs to be handled differently. I'm telling you this because it's important to realize that the error models are different in bosonic encodings. It's not just the standard qubit level error models. There's a richer source of errors, and there's richer ways to handle them. So I want to briefly discuss this one. This is the Gottesman-Kitaev-Preskill encoding. So this is a collection of a superposition of squeeze states. So if you just look at the, let's look at the blue one first. That's the logical 0. This is a superposition of squeeze states. And then there's a shifted version of it. I realize the spike heights are different. Don't worry about the spike heights. The ideal code is infinitely squeezed and all the same. This is an approximation to it. I can tell you more about it. But what the key point that I want to get across is that these spikes at the blue, when shifted, match up with the spikes at the red. And then when shifted again, they go back to the blue. So that means that displacements act like an X gate, a qubit level X gate. And this code actually protects against small displacements. But because all errors are a superposition of displacements, GKP protects against all small errors, some level of protection against them. It's not perfect, but there's some level of protection. So what happens is—
about 4 minutes to go.
All good. So what happens is, if you have a noise process like additive Gaussian noise, where you just kind of blur things out in the wave function, then what happens is, if you stop the process, so once you get to here, you don't have a very good state anymore. Here it's a superposition of mostly 0 and a little bit of 1. But if you stop it here, you can correct the error. So what you do is you take the state in question and you entangle it with a copy of the original 0 logical state, and you do a measurement. And that measurement will give you an outcome and a better quality version of the original state at the price of a displacement. The outcome tells you something about how far it's been displaced, but what you have to guess is whether you need to move it back to the left here or to the right. If you guess correctly, then you have no residual qubit level error. And if you guess incorrectly, you have a qubit level X error. And that's good, because then what we do is we concatenate with a qubit level code, and we can handle the residual qubit level errors. Why bother with GKP? I clearly don't have time to discuss this in detail, but I just want to tell you, I'm going to give you a pitch for why GKP. It turns out it performs the best against loss. It was not designed to handle loss, but it turns out of the known bosonic codes, it performs the best against photon loss. It is also the only bosonic code, only known bosonic code with an all Gaussian gate set. That means it's relatively easy to implement. And this is work from our group here at RMIT in 2019. It's also compatible with scalable CV cluster states, something that we have also worked on. And fault tolerance thresholds exist between 10 and 15 dB of squeezing. And this is challenging but feasible. I've included a reference to a work that really pulls out all the stops and just uses GKP states alone. The thresholds for scalable CV cluster states are on the order of about 15 dB as well when you put those together. And it's been demonstrated in trapped ions and in circuit QED, 2 references here. And proposals exist for an optical demonstration. It hasn't been demonstrated yet, but there's a number of proposals, and they're in the references of this document. So in conclusion, noise and errors are ubiquitous in classical and quantum systems. Protection against them and correction of them requires digital information, for instance, bits or qubits, depending on whether it's classical or quantum. It's best to keep the information encoded while processing and correcting errors, and that means a good code design is critical. Bosonic codes allow this. They enable bosonic error correction. So bosonic modes afford a large Hilbert space in which to encode qubits. The standard photonic qubit is just a type of bosonic code without any meaningful, well, it has an error detection, but it doesn't have any error correction. It can detect loss. Other types of codes offer more protection against noise, so binomial codes, cat codes, GKP, etc. And GKP has a number of advantages and is being aggressively pursued in optics and circuit QED. Thank you.